the equation that quietly predicted the impossible. It began as symbols on a page. No experiment demanded it. No observation required it. Yet this single equation described something that should not exist, a result so strange that even its creator doubted it. And years later, reality would confirm it anyway. To understand why this matters today, we have to look at how equations are usually treated. They summarize what is known. They organize data. They describe reality after the fact. Mathematics follows nature, not the other way around. But this equation did something different. It combined rules that were already trusted and produced an outcome no one was prepared for. Not an approximation, not an error, a clear, unavoidable prediction. The equation insisted that empty space was unstable, that particles could appear without cause, that pairs of matter and antimatter should briefly emerge from nothing, then vanish again. This was not philosophy. It was mathematics doing exactly what was told. At first, this was dismissed as absurd. Nature did not behave that way. Things could not come from nothing. The equation was assumed incomplete or merely symbolic, but it would not go away. Every attempt to fix it preserved the prediction. The impossible was not a mistake. It was a consequence. And slowly, an unsettling possibility emerged. The universe might be stranger than observation had yet revealed. At first, physicists treated prediction as a mathematical curiosity, a side effect of pushing equations too far. After all, equations could suggest many things that never appeared in reality. Nature, they believed, would choose what was reasonable. But the deeper they examined the mathematics, the more rigid it became. The prediction was not optional. It emerged directly from combining quantum rules with relativity. Remove it, and equations collapsed. Consistency demanded the impossible. This created a quiet tension. If the equation was right, then the vacuum was not empty. It was unstable, fluctuating, alive with brief appearances of particles that borrowed energy, existed momentarily, then disappeared without trace. No instrument at the time could detect such fleeting events. So the idea remained theoretical, uncomfortable, but safely untested. A prediction waiting in silence. Years later, experiments grew sensitive enough to notice subtle effects. Forces between objects behaved slightly differently in a vacuum than expected. Energy levels shifted by tiny amounts. Radiation appeared where none should exist. These were not dramatic confirmations. They were whispers, but they matched the equation perfectly. The impossible was leaving fingerprints. What had been dismissed as abstraction was turning into evidence. Mathematics had not followed reality. Reality was following mathematics. And that realization pushed physics toward a conclusion that felt deeply unsettling. The conflict deepened as more evidence accumulated. Each new measurement confirmed a small piece of prediction. Tiny deviations, subtle forces, effects that could only exist if the vacuum itself was active. Empty space was behaving as if it contained something. This forced physicists to confront a disturbing implication. The equation had not just predicted a rare phenomenon. It had exposed a permanent feature of reality. The vacuum was not a baseline of nothingness. It was a restless state, constantly producing and reabsorbing possibilities. This build-up challenged a comforting assumption, that equations describe reality only after it is observed. Here, mathematics had ventured ahead, mapping territory no one had yet seen, and reality was slowly catching up. Emotionally, this was difficult to accept. It suggested that understanding might precede experience, that human intuition was not the gatekeeper of truth, that the universe could be accurately described before it was ever witnessed. The equation also implied limits to observation. These events were not meant to be seen directly. They existed too briefly, too subtly. Reality was happening beneath the threshold of direct detection, yet still influencing everything above it. By this point, the equation felt less like a tool and more like a warning. It was showing that the universe operated beyond common sense, and that logic alone could uncover truths that experience had not yet prepared us for. The stage was set for a final realization. If an equation could predict the impossible, then the boundaries of reality were not defined by observation at all. The climax arrives at a realization that quietly redefines discovery. The equation did not predict the impossible because reality was broken. It predicted it because reality was deeper than intuition allowed. Once confirmed, this insight changed the role of mathematics forever. Equations were no longer just descriptions. They became probes, ways of touching parts of reality that experiments could not yet reach. Logic stepped ahead of observation. This reshaped modern physics. It guided the search for particles, fields, and forces long before they were seen. It explained why empty space behaves like a medium, why nothingness has structure, why the universe is never truly still. More profoundly, it reshaped humility. The universe does not wait to be observed to exist. It follows rules whether or not anyone is watching. And sometimes, those rules reveal themselves first through symbols, not senses. Today, this lesson echoes through every frontier of science. Mathematics is trusted not because it is elegant, but because it has earned that trust. Again and again, it has pointed toward truths that felt impossible until reality caught up. The equation that quietly predicted the impossible did more than succeed. It reminded us that understanding does not always begin with experience. Sometimes it begins with courage. Subscribe to join the journey.